Transformers changed artificial intelligence forever. Everything begins with one simple thing, a token. Modern language models don't process one token. They process thousands, sometimes tens of thousands of tokens together. Here's the hidden problem. Every token tries to compare itself with every other token. As the sequence becomes longer, computation explodes, memory usage explodes, training becomes painfully expensive. But wait, is all of this computation really necessary? What if every token only looked at other tokens that were actually similar? That simple idea gave birth to one of the most elegant transformer architectures ever created. But how does a transformer actually discover which tokens are similar? Let's find out. William James once said, "The essence of intelligence is knowing what to ignore." And surprisingly, that's exactly what Reformer teaches a transformer. Instead of comparing every token with everyone, it learns to ignore almost everything. Imagine you enter a classroom with 100 students. You are looking for your best friend. Would you ask every single student, one after another? Of course not. That would waste a lot of time. Now imagine someone groups similar students together first. Suddenly, instead of searching the entire classroom, you only search inside one small group. That's the central idea behind locality-sensitive hashing. Inside a transformer, words aren't stored as text anymore. They become vectors living inside a high-dimensional mathematical space. Similar words naturally move close to each other. Now comes the clever trick. Instead of measuring every distance directly, Reformer simply throws a completely random direction through the embedding space. Every vector is projected onto this random line. Everything on one side enters one bucket. Everything on the other side enters another bucket. Amazingly, vectors that are already close together usually fall into the same bucket. One random direction isn't enough. So Reformer repeats this process many times. Every random projection generates one more bit. Together, these bits create a unique hash code for every token. Now the transformer simply sorts the tokens according to these hash codes. Similar tokens naturally become neighbors. Instead of comparing every token with every other token, Reformer only compares tokens inside the same bucket. Suddenly, billions of unnecessary comparisons simply disappear. And that's the magic of Reformer. It doesn't try to make attention faster by using a better GPU. It changes the entire way the search happens. But this raises another fascinating question. Why use random projections at all? Haven't we already learned an algorithm that automatically discovers the most important directions in data? In the next section, we'll see how principal component analysis, or PCA, naturally enters the picture. Now let's pause for a moment. Reformer chooses completely random directions to group similar tokens. But shouldn't something feel a little strange? Why random? We've already learned something fascinating. Matrix rank told us that information often lives in fewer dimensions. Singular value decomposition showed us those important directions. And PCA uses exactly those directions to preserve the maximum amount of information. Imagine these are the embeddings produced by a transformer. Every token becomes a point inside a very high-dimensional space. Some directions contain meaningful information. Other directions mostly contain noise. Random projection simply chooses an arbitrary direction. PCA does something much smarter. It looks at the data itself and discovers the directions where most of the information actually lives. Now imagine replacing the random projection step. Instead of projecting onto random directions, we first project onto the principal components discovered by PCA. Then we perform hashing. Intuitively, PCA could create cleaner groups because it preserves the directions containing the most variance. Similar tokens may remain closer together before hashing even begins. But let's be very clear. The reformer paper never proposes this idea. This is simply a research hypothesis inspired by everything we've learned so far. The mathematics suggests an interesting possibility, but it still needs careful experimentation. So, naturally, we arrive at an exciting question. If PCA already discovers the most informative directions in data, why didn't the reformer authors use it? The answer turns out to be one of the biggest engineering challenges in deep learning, and that's exactly what we'll explore next. So here's the obvious question. If PCA already discovers the most informative directions in the data, why didn't the reformer authors use it? The answer has nothing to do with mathematics. It has everything to do with training a transformer. During training, the transformer never stands still. Every gradient update changes the weights. As the weights change, every token embedding also changes. The entire embedding space is constantly moving. Remember how PCA works. It discovers the directions with the greatest variance. But if the embedding space changes after every training step, those principal directions also change. Yesterday's PCA is no longer today's PCA. That creates a new problem. If the data changes continuously, PCA must also be recomputed continuously. Instead of calculating it once, you would need to update it over and over again throughout training. Random projection is incredibly simple. Generate one random matrix, and you're ready to go. PCA is much more involved. It must analyze the data, estimate the covariance structure, compute the principal directions, and then project the embeddings. Think of it this way. Random projection is like taking a lightweight sports car. It may not choose the perfect path, but it's incredibly fast. PCA is like carrying scientific equipment with you. It may provide richer information, but transporting that information comes at a cost. This is exactly why reformer chooses random projections. They are extremely fast, easy to implement, and surprisingly effective. Sometimes, an approximation that is fast enough wins over a mathematically elegant solution that is too expensive to maintain during training. But what if there were a way to update the principal directions continuously without recomputing everything from scratch? Could we combine the mathematical intelligence of PCA with the efficiency of reformer? That question opens the door to an exciting research direction. Every great research paper answers one question, but creates many new ones. Reformer solved the problem of efficient attention using random projections. But what if we could somehow combine the intelligence of PCA with the efficiency of reformer? Instead of recomputing PCA from scratch after every update, Imagine making tiny adjustments as new training batches arrive. The principal components would gradually evolve together with the transformer. One possible idea is to insert incremental PCA before locality-sensitive hashing. Instead of random directions, the hashing process would receive directions that continuously adapt as training progresses. Or maybe replacing random projections isn't even necessary. What if random projections provide exploration while PCA provides stability? A hybrid projection system might combine the strengths of both. Would this improve accuracy? Would it reduce memory? Would training become slower? Right now, nobody knows. These questions can only be answered through careful experiments. This is exactly how AI research moves forward. Every paper inspires new questions. Some ideas fail, others change the entire field. Progress happens because researchers keep asking, what if? The reformer paper is not the end of the story. It's one milestone in a much larger journey toward making transformers faster, smarter, and more efficient. And this raises an even bigger question. If reformer is only one solution, what other brilliant ideas have researchers invented to make transformers dramatically faster? That's exactly where we're going next. Today, we uncovered one of the most elegant ideas in transformer research. Instead of comparing every token with every other token, reformer intelligently groups similar tokens first. A simple idea with an enormous impact. But reformer is only one chapter in a much bigger story. Researchers around the world have proposed many completely different ways to make transformers faster, more memory efficient, and scalable to millions of tokens. Some compress the attention matrix. Some approximate similarity using mathematical kernels. Others redesign the computation to fully utilize modern GPUs. Every architecture solves the same problem, but in a completely different way. And this evolution is far from over. Every year, researchers continue discovering new mathematical ideas that push transformers even further. In our next video, we'll explore a completely different idea. Instead of grouping similar tokens, what if we could compress the entire attention computation using low-rank mathematics? We'll discover how matrix factorization opens another path toward efficient transformers. Until then, stay curious, keep learning, and I'll see you in the next one.